In this video, we're turning our attention to solving systems of inequalities. I'm going to go through 4 examples that involve linear and absolute value inequalities within the systems, okay? So solving a system of inequalities, it's just like solving a system of equations in that you're trying to find all common solution points, okay? So in terms of system of inequalities, what that means is we're looking for the overlap of the shaded regions between the different inequalities of the system, okay? So in this first example, we have 2 linear inequalities. All we need to do is graph both of them in the same coordinate plane and look for their overlap, okay, of the shaded regions. So I'll do the inequality in red first. That's in slope-intercept form, so I'll graph the boundary line, y-intercept of -3, rise 2, run 1 to the right, fill up the graph, and that would be a solid boundary line. Okay, and I'm going to do a test point here. I would use the origin. If I plugged 0 in for x and 0 in for y, that would lead me to 0 is greater than or equal to -3, which is true, right? So that means since the origin is to the left of this boundary line, I would be shading all of this side, this half plane. Okay. And I'm not going to get crazy on my shading here because I just don't want too much on my graph in the end. Okay. All right. Next inequality is in standard form. I'll graph both the x and the y-intercepts first here, which are both at 2. Okay, and from there you can see really the slope reduces to -1. So I can just fill in some more points here. And then this would be a dashed boundary line, meaning the points on this line are not actually part of the solution set. And I would do the same thing with a test point of the origin. That would lead me to 0 is less than 2, which is also true. So that tells me I would be shading over on this half plane for that line. Okay, so now we're looking for where does red and blue intersect or overlap. You can see that would be this section right here. All right, and there is my solution set. What's in green? Pick any random point in that area, and it should satisfy both inequalities of the system, just like the origin did. Okay. All right, moving into example 2. So in this example, the red inequality is linear, but now the blue inequality is an absolute value inequality. Okay, so that graph's going to look a little bit different. So let's do the linear inequality first. It's in slope-intercept form. -2 for the y-intercept, up 1, right 2 for the slope, or down 1, left 2, dashed line, or I'm sorry, a solid line. Nope, I'm on the wrong. I got to switch over to this. All right, plugging in the origin for x and for y will give me 0 is greater than or equal to -2, which is true. So I'm shading this half plane. Okay, now for the absolute value inequality, recall absolute value equations that have one variable or 2 variables, they graph to be v's, right? And the v has a vertex. So I can identify the vertex here to be the point 1, 3, right? I'm using this number and this number to come together to make the coordinates of that vertex. So I will plot that first. All right, and then I can use my A value here to help me determine the steepness of each half of the V. And I'm also noticing that we're negative. So from this point, I'm just going to go down 2 units and right 1, or down 2 and left 1. And I can just keep doing that as much as I can fill up the graph. So there would be my set of points to help form the V. This V would have to be dashed. So the points on the V are not actually part of the solution set. Okay. All right, so at this point, I need to shade for that inequality. I can use the origin as a test point. The origin is just inside the V. So plugging, let's actually show the work on this one. So if I plug 0 in for X and for Y, that's going to lead me to 0 minus 1 is -1, but then you have to take the absolute value of that to give you +1. And you're going to end up with 0 is less than 1, which is true, right? So that means for the V, we're shading on the inside portion of it. Okay. And now we can see the overlap is in the triangular region in there. Okay. And there we go. There's our solution set. Okay. All right, example 3. At first glance, this is going to seem like it's essentially the same type of system as the previous example. You have a linear inequality in red. You have an absolute value inequality in blue. Notice, though, the absolute value inequality, it only has one variable, not 2. So that's going to make things a little bit different, okay? Let's start with the linear inequality. Y-intercept of 1, slope of -1, and this would be a solid boundary line. Okay. Using the origin, I would end up with 0 is less than or equal to 1, which is true, so I'm going to shade this half plane that includes the origin. Okay. And now for the absolute value inequality. Since it's only in one variable, I need to break this up into a compound inequality that has 2 cases to it. So the first case would be x plus 1 is less than 3. Then I'm going to need the word and, followed by the negative of x plus 1 also has to be less than 3. So this side's going to solve to x is less than 2. I'll divide the negative over here, make that greater than -3, and then x is less than 2 and x is greater than -4. Okay. All right, now how do I graph that? Well, I essentially need vertical boundary lines at both 2 and -4, and each of these would be dashed boundary lines. So there's x equals 2, and then x equals -4. So we're supposed to be less than 2, so any point whose x coordinates are less than 2, but also any point whose x coordinates are greater than -4. That would be all of the points in between those 2 boundary lines. Okay. So now we can see where our overlap occurs. It's in this region right here. And there you have it. This absolute value inequality included x plus 1 is less than 3 had it been absolute value of y plus 1 less than 3, really the only thing that changes is instead of vertical lines at 2 and -4, you would end up with horizontal lines at y equals 2 and y equals -4. All right. One final example here. Let's see what happens on this. Now we're back to a linear system of inequalities, both of which are in slope-intercept form. The inequality that's in red there, y-intercept is 1, slope up 3, left 4, or down 3, right 4, solid boundary line. Okay. For shading, if you use the origin, you'll end up with 0 is greater than or equal to 1, which is false. So I'm going to shade the half plane that doesn't include the origin, which would be this one right here. Okay. Move to the second inequality, y-intercept of -2. And then the same slope as the other boundary line, so up 3 and left 4, or down 3, right 4. This boundary line will be dashed. Okay. Now you might be thinking that with the lines being parallel to each other, that automatically makes your system no solution, but not necessarily. It just depends on where the shading is for the second inequality. So if I use the origin again as my test point, I'll end up with 0 is less than -2. That's also false. So I'm going to shade the half plane that doesn't include the origin, which would be this one. Okay. So since I ended up shading on that side, I don't end up with any overlap between the red and the blue shaded regions. Okay. So that does mean that there is no solution to this system. Okay. So you definitely want to make sure you state that somewhere off to the side. We're going to say no overlap, thus no solution to this system. All right. So that's it for this video.